Hi, welcome back. So, we were trying to non-dimensionalize, basically develop the boundary layer equations from the Navier-Stokes equation, right? We started doing that. So, we kind of stopped here, at a very interesting junction where we had non-dimensionalized the velocities, the time, as well as the lengths, which is x, y, and so on and so forth, right? So, now what is interesting is that so we kind of stopped here. Now, we will do just simple few things. Now, if you see rho v infinity square, right. So, rho v infinity square is nothing but the dynamic pressure, twice the dynamic pressure, right. So, we can use this to another way of looking at that is just find out the dimensions of rho v infinity square, do it yourself. Okay. So, see if that will match the same as pressure. So, that if I divide the pressure by rho infinity square, then it becomes non-dimensionalized, and again L is here, that can go down to L. So, this term that we had, the pressure term, so this also I can write as so basically all I am saying is that if I were to write this, that P by rho v infinity square is P star, right. So, therefore, I will take this off, okay, and this becomes P star by x star, right. This. Now, I do not know if you have already noticed or know that what does this mean? This term here that you see, what does this ring a bell? What is this term? Okay. Now, if you remember, what is Reynolds number? Rho v L by mu. So, what is this? This is nothing but 1 by R e. It is nothing but 1 by R e, right. So, we have come up with some equation, which has which has the Reynolds number included, and that is important to us, right. Because we did say that the boundary layer behavior depends on Reynolds number, right, whether it is laminar, turbulent, or even creeping flows which Reynolds number less than 1, so on and so forth. So, Reynolds number is now included, right. Is that a good thing or a bad thing? We will find out very soon. So, having said that, so let me therefore write down this equation finally. So, that is del. So, basically we are going from there to here. So, we are going to write this as del u star del t star, okay, plus u star plus v star del u star star, okay, is equal to minus del p star del x star plus 1 by R e del 2 del x star square. I do not know if you have noticed, instead of the x I wrote, I was drawing a star there, silly, okay, u star plus del 2 del y star 2 v, right. So, this is essentially, so this is nothing but, so this is the essentially the Navier-Stokes equation or momentum equation, right, in the x direction. So, this is nothing but the momentum equation in the x direction, let us call it 1, right. So, now so this is, let us write it, momentum equation in x direction, right. So, we got this thing. So, if you see the nature of this equation, we should be able to just look at this equation and write out the momentum equation in the y direction as well, right. So, all we need to do is change this u. So, if I were to do that, how would I do that? So, that would be del v star del t star plus u star del v star del x star plus v star del v star del v, this thing is equal to minus del p star del y plus 1 by r e del 2 del x square v star plus okay, I think I made a mistake here. Okay. Oh, sorry. I wrote this as this term here as u by v. This is still u, sorry. It is u star. Yeah, it's u star. It's not v star. There's no v term here actually. Okay. U star, and this is also u star plus, forgive me for that. Okay. Okay. So, oh sorry, yeah, this was the second equation. So, this has to be v here. So, this also has to be v. So, here it is v star, here it is v star, right. So, this equation is therefore, so this is the momentum equation in the y direction. Okay. Okay, right. We will do something else. So, along with this, we also need the continuity equation, right. So, what is the continuity equation as we know it? So, the continuity equation is nothing but d rho dt plus basically divergence of rho v is equal to 0. Right. Now, this is let us take a steady case. Okay. So, then this term will go away. Let us take it incompressible, so that this rho term can be can be taken out of that. So, finally, what we are left out is basically divergence v is this, right. So, which in 2D essentially means del u del x plus del v del y is 0, right. So, if I again normalize this, right, how will I normalize this? I will multiply this entire equation by L by v infinity, right. So, if I do that, the u and the v can get normalized by v infinity, and the x and the y can get normalized by the L. So, that we get del u star del x star plus del v star del y star is equal to 0, right. So, this is essentially the continuity equation, right, and let us call this and this. So, therefore, this is continuity, right. So, now what you see is that from the starting point, we come up with these equations. Now, what we will do is we will take a breather and look at these equations. So, we have been able to do all this. Okay, we have been able to do all this. We have introduced the Reynolds number. What does this even mean? Now, if you look at this, right, if you let us now just concentrate on these 3 equations. Okay. Now, if you see here, right, that now let us bring in a little bit of our knowledge of boundary layers so far, and we have said, right, that the boundary layer thickness, okay, boundary layer thickness is is a function of kinematic viscosity, right. So, kinematic viscosity and delta by L, okay, is a function of 1 by root of R e, right. And okay, of course, delta is much smaller than L. Now, if you see this here, now what does this tell you? What does this tell you? That here, so a boundary layer, thickness is inversely proportional to the Reynolds number, to the square root of the Reynolds number. So, if the Reynolds number here is very large, right. So, say Reynolds number tends to this, right, then what happens, right? Then what happens is that the boundary layer thickness tends to 0, right. So, then this means that boundary layer thickness tends to 0. Okay. Now, boundary layer thickness tends to 0, and the boundary layer thickness depends on the kinematic viscosity, right. So, if you look, the reason I am saying all these things is that numerically, the viscosity effect, right, into the equations is accounted for by these terms, right, these two terms, the second terms on the right hand side of the two momentum equations. And what we are saying here, see we do not have a viscosity term here, we've got rid of the mu, we do not have that anymore, right, but we have a Reynolds number. So, what we are saying is that if the Reynolds number, right, there are a couple of ways of looking at this. So, you can straight away say, what is there to talk so much? I mean, increase the Reynolds number, so anyway this will go. True, that is true, but I'm trying to understand this more from a physical point of view also. That is this. So, the point is, if the Reynolds number is very large, right, if the Reynolds number is very large, then the boundary layer thickness is very small, nearly 0. And that means that now boundary layer thickness also is directly proportional to the viscous to the kinematic viscosity, which means that itself is sort of is not affecting the flow anymore. So, which essentially means that large Reynolds numbers, these two terms are going to vanish, or are going to be negligible, or in the sense that it will not contribute to the equations in any way. Now, if that happens, if you then look at these equations, so basically they reduce to the inviscid case, right. So, the whole lesson out of here is that at high Reynolds number, okay, the equations 1 and 2, okay, reduce to the inviscid case, right. And this is solely from this consideration. This is from this consideration that we are talking about. Okay. So, which means, right. So, which means that for very high Reynolds numbers, right, for very high Reynolds numbers, these equations, the equations 1 and 2, the non-dimensionalized equations, if you try to use these equations very close to the surface, okay, say surface of a plate, it is not going to make much of a difference, because this can only account for the inviscid case. So, it cannot take into account viscous effects. So, even if you use this, okay, it's basically is going to mean that for very high Reynolds numbers, this term is anyway going to go to 0. So, the solution that you get will have no bearing, or will not be able to account for the boundary layer or any viscous effects at all. Okay. Now, that is a problem because we were hoping to take these equations and bring them to a form where we can solve them near the boundary layer, right? So what do? Okay, do we give up? Well, no, we won't. Let's see what else we can do to get around this problem. This is a problem we've kind of brought upon ourselves, right, by doing this. Now, so we've got to find ourselves a way to get out of this. Okay, so let's see. And so basically all we have to do is make sure that at high Reynolds numbers, right, which is like the limiting case here, that these terms don't disappear. So what do? Okay, I don't want anything to disappear, because if that disappears, then my whole thought process falls through. I can't do anything with it. So that's my purpose. So now, what is important here? So when I say that disappears, so in the sense that in these here, there's something called order of magnitude, right? Order of magnitude. So basically, so if two things have the same order of magnitude, it essentially means that they are pretty much of the same size, And why do I do that? Because it helps me to compare values. Okay, for example, you have this instantaneous term here and this V star convective term here. Now these two values, unless and until they are comparable, then they have to be comparable to really make any sense to this entire equation. Now if one of these terms, whichever, doesn't matter, is like so minuscule, so small, so that doesn't contribute here, then it might as well be taken out, right? So which we can do, but what that means is that then I cannot take care of the boundary layer. But then what I set out to do is to develop boundary layer equations, which is what I want to study. So therefore this is a problem. Okay, I did a nice job of non-dimensionalize everything and so on and so forth, but I can't use this in the boundary layer. So let us see what we will do. The first things first, what we will do is that we will assess the order of magnitude, okay, order of magnitude of each term, right, in this equation. Now, if you see here, okay, x star, what is x star? So if I go here, okay, I can use this space actually. Now x star. Now x star is essentially x by L, right? Now what you need to understand is that x, right, that the boundary layer is developing along x, right? So the maximum value of x can be L, right? That's the length of your plate. So therefore x by L, which is equal to x star, has an order of 1. It's of the order 1. Okay, so in the sense, another way of looking at that x is, you can think of x in terms of the distance L. Okay, so it's of the order 1. Then similarly, u star, okay, u star is nothing but u by v infinity. So again, this is also of the order 1, right, because you could take the value v infinity, right, that's the maximum that it can take. So it is of the order of v infinity, right. So therefore it is order 1. Okay. Now another thing is, if you look at this Reynolds number, right. Now as Reynolds number is okay, fine. So u star. Now another thing is y star. Okay. Now y star is basically y by L. Y by L, but what we would like to think is that what is the order of y star? What is your idea? What should be the value of what should be the order of y star, right? This should be the order So the way to look at this is what is the maximum value of y that we should be looking for, because we are trying to study the boundary layer. So the maximum would be delta, right. So delta by this, so which means this is delta star. So that means the order is of delta star, right. So y star is of the order delta star. Okay. Y star is the order delta star, so that now if that is so, okay, if that is so, right, now we have this term del v star del y star in the continuity equation. Now if you see that as Reynolds number tends to infinity, or Reynolds number is very large, right, the boundary layer thickness also tends to 0, which means that delta star tends to 0. If delta star tends to 0, then what happens to this derivative, which is del y star, because y star is of the order delta star, right. So then the continuity equation itself becomes degenerate, right. So we need to do something about that. So numerically this is becoming degenerate. So how do I tackle that? Well, the way to one of the ways to prevent this is that we also make v star, right, is of the order of the same order as y. So we say that v star, okay, is also of the order of delta star, right. So that this to prevent the continuity equation from becoming degenerate, right. So now let us do one thing. Let us write the order of magnitude of each term in the momentum equations, right. So let me write it here. So if you see, right, so u star the order is 1. What about t star? The order is 1. So the order of this term is 1. Okay. Then the order of u star is 1. Okay. The order of del u star, this is also 1. Okay. Now v star. Now v star is of the order delta star, right, and del u star order is 1, okay, and y star is order delta star. Is that fine? Okay. And we are now going to go there, R E, and this is again u star. Okay, what about R E? Okay, we'll come to that. Now u star the order is 1, okay, and x star is also 1. So this is 1. V star is order of delta star, and sorry, this is u star. So that is 1, and y star is of the order delta star. So this is delta star square. Okay. Now what about R E? Okay. So R E is rho v d by mu, right. So R E, this, and what should be the order of that, right. So what should be the order of the R E? So in my opinion this should be of the order delta star square. Okay, you can cross check that. Okay, so R E is basically actually yeah, so 1 by, yeah, so essentially yeah, this, if you want to look at that. So that 1 by R E, so the order is delta star square. Okay. So if I do that, okay, if I write that. Now let us go to this, the second equation, and see what we get. So here V star, so this is, the order is delta star, T star is 1, U star is 1, right, del V star del X star is del star, because X star is 1. Again this is this. Del V star, well, V star is order of delta star, Y is also order of delta star, so this is 1. Okay. Then again this one is delta star. Okay. This is order of delta star. Okay. And this is order of 1 by delta star. Yeah, well, you know, yeah, correct. And this is 1 by delta star, right. Now, if I have that, okay, if I have that, so now okay. So now, you know, of course, you know, we've done this. So what we're going to basically now say is that we need to do something, we need a different, you know, so we need to do something so that we can retain the viscous terms of this equation. Now, as Reynolds number tends, you know, to infinity, right, or Reynolds number is very large, so y star is basically delta star, right. But then if y star is of the order delta star also becomes very less with increasing Reynolds number. So therefore, at high Reynolds number, we cannot use this description of y star, right, because y star also will become very less, you know. So what we're going to do is that multiply, okay, this y star values by something so that, you know, we can increase its value, right, given in the equation. So what, and the way we are going to do that is by using this transformation, so that y star, okay, I am going to multiply by under root of R e, and v star, right, because again multiply by under phi. And what I get here is y bar, and what I get here is v bar. Okay. So now if you see, okay, now if you see what is the order of y bar, right. Now y star, the order is delta star, okay, and Reynolds number is 1 by delta star. So here it will be 1 by delta. So therefore, the order of y bar is 1, and similarly the order of v bar is also 1. In that case, this is not going to, this whole thing is not going to go, you know, degenerate anymore, right, and also the viscous terms are not going to go away, you know, as long as I multiply this by R e. Right. So if I do that, right, if I do that, and I am going to introduce this, right, this expression into these 1, 2, and 3. So basically what I am going to do is, therefore, you know, take this new non-dimensionalized form y star this, y bar and v bar, and change the y star, right, and v star to y bar and v bar, right. If I do that, what I get finally, so I am going to do that for all the 3 equations. I am going to do that for all the 3 equations, 1, 2, and the continuity equation. If I do that, what I get is this. So I can write out the equations at okay, plus we introduce v bar, this, that, okay, that is the x momentum then the y momentum completely reduces to that, okay, and the continuity okay. So essentially, so now what, so we're going to stop here now and pick this up again, in the next module. So what we've now been able to do is get these equations to a point where they look like this. We did the non-dimensionalized equations now look like this, right? And we've accounted for, so here there is no chance of, any term, the viscous terms being neglected or anything like that. So we're going to discuss this. So this is basically, let's say, okay. So let this be, so essentially what we're saying is that, the y star and the v star have basically been stretched by a power of the Reynolds number, which in this case is half, right. So because we've stretched it by root of R A. So let me stop here, okay, and we're going to pick this up again and see that what from where do we go from here. We've not yet reached the boundary layer equations, and it is interesting if we can make further simplifications to this, and there are some inferences to be drawn from here, which is interesting, and the simplicity will start showing, or rather the simplification to the Navier-Stokes equation and how it applies to the boundary layer will start showing now. Okay. So of course they look much simpler compared to where we started with, you can see that, but let's discuss this when we get to the next module. Okay. Thank you.